Memory mappings. That's what we're doing today, or this morning, I should say. It's memory mappings, chapter 49. I've been thinking a little bit about the progress that I've made on this book and how I want to approach finishing it. Yesterday, I kind of blasted through all the System V stuff: intro, message queue, semaphores, and shared memory. And I skipped over, some of the minutia details about like limits. Like once you understand there's limits for all these object types, it doesn't really make sense to dive into all the details of each limits. And same thing with the associated data. It's like, okay, I understand there is this associated data that's attached to the object. Like I don't need to spend 20 minutes reading about every single object type's associated data. So I did skip over a good bit of, especially the shared memory data structure, associated data structure, and limits. I was thinking this morning, I was like, that was really unsatisfying that I skipped over those things. I know that they're not going to be helpful for me because System V IPC is kind of like, it was legacy at the time of writing this book, and this book was published in 2009, I think. When was the publication date on this originally? 2010. It's been almost 16 years now since this book was published, and it was legacy at the time of publication. So it's like, I think I'm justified to skipping over some of the details of that. But now that we're getting into some other topics that aren't legacy, things like POSIX IPC, which is very similar to SysV IPC, memory mappings, virtual memory operations. I feel like those are things that I want to take time with and do more experimentation. Just feel like, I should have more time with those topics. So I'm going to slow down my reading. Today, my goal is just 50 pages. Previously, my goal has been 100 pages a day. 100 pages a day is doable if all you're doing is reading and you're spending the entire day doing it. I'm willing to dedicate the time, but I'm not willing to dedicate or sacrifice, I should say, the amount of focus and experimentation that I'm giving the subject. So moving forward, I'm going to be slowing down a little bit. My goal still is to finish this book by the end of January, which gives me until Saturday. And if we look at our progress, we are on page, 1017. So there are 1400 minus 1017. So that's 383 pages left. And if we divide that by how many days we have left, which are 1, 2, 3, 4, 5, technically 5, but even 6, because I wouldn't mind doing some reading on Sunday if I have to. But it'd be 1, 2, 3, 4, 5 days. So that's 76 pages a day for me to finish by Saturday. Friday, I have a bunch of social stuff that I have to do. So it's going to be and I have a bunch of stuff on Friday. So I probably won't be able to get as much dedicated time to reading on Friday. Check my calendar for the rest of the week. Let's see here. Tomorrow is going to be compromised as far as the amount of time I have. Although I don't have training in the morning, so I can have more time in the morning. So tomorrow might be about even. And then Friday is going to be a little compromised as well. So I guess my goal should be about 75 pages a day, roughly. But I'm just gonna go my own pace here, and if I feel motivated to do some experimentation with something, I'm gonna do that. I'm not gonna just like bulldoze ahead. Now that we're through the System V IPC stuff, which is like super legacy, I feel like I want to slow down and not rush it, because I can still finish even if it goes to Sunday. Like say I give myself 6 days instead of 5 days. Oops, that's the problem with using underscore, is you have to do like that. So that's around 63 pages a day for me to finish by Sunday. And that doesn't include the appendices, which shouldn't be a lot more, but I think it's about right. So 60 to 75 pages a day, and I'll finish by this weekend. That feels good. I mean, I wanted to finish by Thursday, and that's still totally doable. Thursday would be 1, 2, 3 more days of reading, which would be 127. Which, to be honest, I don't think it's doable at this point. I can do 127 pages a day, but it's just like, I feel bad at the end of the day. I feel drained. I feel like I haven't given the topics a lot of like time, the time that they deserve. So yeah, I'm gonna extend it to Saturday, and then if I have to, Sunday. So that means 75 pages a day, and then if I slip on that goal, then I have Sunday as like a backup. That feels good to me. All right. Cool. I guess we can get started here with memory mappings. Let me make sure my task manager is up to date here. It's not. So TN T789. So we're on 49, which is 11. So we can say all those are done. Okay. So now we're on 49. So it takes us to 73% complete. Whew. Yeah, all that System V IPC stuff, I'm glad that I went fast through it. And I'm glad that I spent the time to at least read those chapters and not just skip over them. Because now I know like how to like list IPC objects in the kernel, which they don't have a file system representation, so it's nice to know like where to go to find, you know, where to list these things. And I can remove things with I think it's IPCRM, and then you say in my case it'd be mem7 SHM yeah, IPCs, there you go. So you know how to like remove them and get information about them. And I did write a few programs kind of experimenting with them. All right, let's go ahead and open up our progress. We're just going to copy over here 1016 at 10:09, and yeah, let's get started on that. Memory mappings. This chapter discusses the use of mmap or mmap system call to create memory mappings. Memory mappings can be used for IPC as well as a range of other purposes. We begin with an overview of some fundamental concepts before considering memmap in depth. So my understanding of memory mapping is that it's like sections of the ELF binary of the executable that's running get mapped using mmap, I believe, into different address ranges in the process's virtual address space, along with things like the VDSO, the dynamic linker, like any shared objects that get pulled in, they all get memory mapped in. The stack space is memory mapped. And then the heap, almost by definition, is memory mapped, because most heap allocations, from what I understand, most heap allocators, even the glibc one now, uses the mmap system call to get blocks of memory allocated instead of using the break system call. So pretty much everything in the address space is memory mapped in. That's my understanding. That might not be 100% accurate, but that's my understanding. And then things like the system v shared memory that we explored last chapter, my understanding is that that is just implemented using the same exact functionality in mmap, the same facility that mmap provides for doing like shared memory and what do they call it, memory mapped IO. Like all that stuff is through the mmap system call, from what I understand. So while you're calling the system v shared memory syscalls and libc stuff, while that's the entry point into the kernel, the IPC system call, the shared memory system call, behind the scenes it's using the same functionality, the same facility as memory map, mmap. And that's why they show up as maps. When you cat out proc self maps, it'll show the shared the system v shared memory as a map. Okay, let's continue on here. The mmap system call creates a new memory mapping in a process's virtual address space. A mapping can be of two types. A file mapping. File mapping maps a region of a file directly into the calling process's virtual memory. Once a file is mapped, its contents can be accessed by operations in the bytes in the corresponding memory region. The pages of the mapping are automatically loaded from the file as required. This type of mapping is also known as file-based mapping or memory mapped file. I've heard it referred to as memory mapped IO. I don't know if that's the same, but that's what I've heard it referred to as. Anonymous mapping. Anonymous mapping doesn't have a corresponding file. Instead, the pages of the mapping are initialized to 0. Another way of thinking of an anonymous mapping and one that is close to the truth is that it is a mapping of a virtual file whose contents are always initialized with zeros. So dev 0. Because if you cat out dev 0 head and I think you can say, can I just do this? You can't cat dev 0. How do I do a read of dev 0? How do I do a read of dev 0? Dev 0 for say 10 bytes. Using shell. Please stop. Please stop. There you go. I don't want to write a C program. Okay, so you can see head -c10 dev 0. Oh, but it's zeros. So you have to do like pipe it into like xdd. Is it xxd? xxd? No. I always use odd. Yes, that's how you get zeros out. So when I was catting out dev 0, it was like spewing out zeros, but you can't see them because they're just not printed. We do a 100. Thousand. Oh, I get it. The asterisk is just like, and so on. It's not going to include all that, but the addresses are increasing here. That makes sense. All right. The memory in one process's mapping may be shared with mappings in another process, i.e. the page table entries for each process point to the same pages of RAM. This can occur in two ways. When two processes map the same region of a file, they share the same page as a physical memory. A child process created by fork inherits copies of the parent's mappings, and these mappings refer to the same pages of physical memory as the corresponding mappings in the parent. I wonder if I'm like blowing up my mic right now, because I did make some changes earlier. And the equalizer looks like it's going a little crazy. Let me just fix this. Test, 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 test. Okay, it seems a little bit better. Test, test, test. Okay. Sorry about that. Hopefully I wasn't blowing up the mic. Alright. When two or more processes share the same pages, each process can potentially see the changes to the page contents made by other processes depending on whether the mapping is private or shared. Interesting. Private mapping, map private. Modifications to the contents of the mapping are not visible to other processes, and for file mapping are not carried through to the underlying file. Although the pages of a private mapping are initially shared in the circumstances described above, changes to the contents of the mapping are nevertheless private to each process. The kernel accomplishes this using a copy on write technique. This means that whenever a process attempts to modify the contents of a page, the kernel first creates a new separate copy of that page for the process and adjusts the process page tables. For this reason, private mapping is sometimes referred to as a private or copy on write mapping. Shared mapping. Modifications to the contents of the mapping are visible to other processes that share the same mapping, and for file mapping are carried through to the underlying file. The two mappings attributes described above, file versus anonymous and private versus shared, can be combined in 4 different ways, as summarized in table 49.1. So you have a private file mapping, initializes memory from the contents of the file, but then changes are not flushed out to the file. You can have a shared file mapping, which is memory map.io. Again, that's what I heard it referred to as, which you can also use for shared memory between processes. An anonymous shared mapping, which is just used for IPC, and an anonymous private mapping, which is for memory allocation. That's local to the process. So that's like, that'd be kind of like malloc, like a heap allocation type thing. The 4 different types of memory mappings are created and used as follows. Private file mapping. The contents of the mapping are initialized from a file region. Multiple processes mapping the same file initially share the same physical pages of memory, but the copy on write technique is employed so that changes to the mapping by one process are visible to the other processes. The main use of this type of mapping is to initialize a region of memory from the contents of a file. Some common examples are initializing process text and initialize data segments from the corresponding part of a binary executable file or a shared library file. Private anonymous mapping. Each call to mmap. Private anonymous mapping. Each call to mmap to create a private anonymous mapping yields a new mapping that is distinct from, i.e. does not share physical pages with, other anonymous mappings created by the same or different processes. Although a child process inherits its parent's mapping, copy and write semantics assure that after fork or clone, the parent and child do not see changes made to the mapping by the other process. The primary purpose of private anonymous mappings is to allocate new zero-field memory for a process. malloc employs mmap for this purpose when allocating large blocks of memory. Sharing file mapping. What's interesting is that it's zero initialized, which I would assume would be kind of costly to do. Shared file mapping. All processes mapping the same region of a file share the same physical pages of memory, which are initialized from a file region. Modification to contents of the mapping are carried through to the file. This type of mapping serves two purposes. First, it permits memory mapped I/O. By this we mean the file is loaded into a region of the process. Virtual memory modifications to that memory are automatically written to the file. Thus, memory mapped I/O provides an alternative to using read and write for performing file I/O. A second purpose of this type of mapping is to allow unrelated processes to share a region of memory in order to perform fast IPC in a manner similar to System V shared memory segments. Shared anonymous mapping. As with a private anonymous mapping, each call to mmap As with a private anonymous mapping, each call to mmap to create a shared anonymous mapping creates a new distinct mapping that doesn't share pages with any other mapping. The difference is that the pages of the mapping are not copy and write. This means that when the child inherits the mapping after fork, the parent and child share the same pages of RAM, and changes made to the contents of the mapping by one process are visible to other processes. Shared anonymous mapping allow IPC in the manner similar to System V shared memory segments, but only between related processes. Interesting. So you can't have arbitrary processes attaching the shared memory segments if they're anonymous. If they're file-based, then you can attach them, but you have the performance issues of needing to flush out all of the I/O to like a hard drive. So there might be some way of like preventing that, but that would be certainly a performance cost there. I'm gonna go grab some water because I'm gonna be here for a while, and I don't want to get too dehydrated here, so I'll be right back. Okay. I'm also going to clip my nails while I read here just because it's annoying to me. Alright. We consider each of these types of mappings in more detail in the remainder of this chapter. Mappings are lost when a process performs an exec, but are inherited by child of a fork. The mapping of type private or map shared is also inherited. Information about all of the process mappings is visible via the Linux specific proc-pid maps file, which is described in section 48.5. Did we? Let's go back to 48.5. I don't remember. I guess we kind of discussed that, yeah. Location of shared memory and virtual memory. Yeah, we went over the maps file, yeah. Okay. One further use of mmap is with POSIX shared memory objects, yeah. Which allow a region of memory to be shared between unrelated processes without having to create an associated disk file, as is required for shared file mapping. We describe POSIX shared mapping objects in Chapter 54. That's the one that I'm curious about using. Because it's kind of like System V's shared memory, but it's the POSIX version. Creating a mapping, mmap. Mmap system call creates a new mapping in the calling process virtual address space. So we got the mmap system call. You give it an address. It's probably going to be optional. You give it a size that you want. The prot, which I'm not sure what that is, protocol maybe. Flags, file descriptor, offset, lots of things. Let's see, the adder argument indicates the virtual address at which the mapping is to be located. If we specify adder as null, the kernel chooses a suitable address for the mapping. That makes sense. This is the preferred way of creating a mapping. Yeah, I can't really envisage a use case that I would have for wanting shared memory or a mapping of any sort at a specific address, unless the pointers that were stored in the memory require a specific address, because they're like global pointers, like they point to specific addresses in memory. Then I could see you wanting to like map to that specific area, but there's no guarantee that that's going to be available. Like some other thing could come in, like loading a dynamically linked object or a heap allocation, and reserve those addresses for itself. So the better thing to do is like what we did yesterday, which is any pointers that you store inside the mapped region need to be relative, basically offsets of the base address of where the map starts. And then you have to do a little math to add the base to the offset to figure out the actual global address. But yeah, I can't really think of any other use case. Actually, my audio is clipping again. Let me try and fix that. I don't want it to clip, but I also, like, when I listen to my recordings on YouTube, they're always like my voice sounds so much lower than the voice levels for other videos that I load up. So that and then they don't clip. So I don't know what that means. I'm not an audio guy, but I'd rather be a little bit lower decibel level and not clip. Okay. Oh, did we get messed up here? Here we go. Yeah, sorry, I was on the wrong page there. Alternatively, we can specify non-null value in adder, which the kernel takes as a hint about the address at which the mapping should be placed. In practice, the kernel will, at the very least, round the address to a nearby page boundary. In either case, the kernel will choose an address that doesn't conflict with an existing mapping. If the value map fixed is included in flags, an adder must be paged align. We described this flag in section 4910. On success, mmap returns the starting address of the new mapping. On error, mmap returns map failed. On Linux and on most other Unix implementations, the map failed constant equates to a void star of -1, which is all Fs. However, susv3 specifies this constant because the standards can't guarantee that void star -1 is distinct from a successful mmap return value. That might actually be why address ranges are limited in practice. The length argument specifies the size of the mapping in bytes. Although length doesn't need to be a multiple of the system page size as returned by sysconf page size, the kernel creates mappings in the units of sizes of this size, so that length is in effect rounded up to the next multiple of page size. The prot argument is a bit mask specifying the protection, that's right, protection to be placed on the mapping. It can either be none or a combination of any of the other three flags listed in table 49.2. So we got none, which just means it's completely unprotected, raw dog in it, and then we got read, write, and exec. Read means that the contents of the region can be read, write allows for writes, and execute means that the instruction pointer can be located in that address range. The flags argument is a bit mask of options controlling various aspects of the mapping operation. Exactly one of the following values must be included in this mask: map private and map shared, which we already went over, but we'll read again. Create a private mapping. Modifications to the content of the region are not visible to other processes employing the same mapping, and in the case of file mapping are not carried through to the underlying file. Shared. Create a shared mapping. Modifications to the contents of the region are visible to other processes mapping the same region with the map shared attribute, and in the case of file mapping are carried through to the underlying file. Updates to the file are not guaranteed to be immediate. See the discussion of msync system call in section 49.5. So they basically have an equivalent of the sync system call called msync. And if we man up our syscalls and look for sync, so we got our fsync there. We got fdatasync, which syncs the data, the changes to data, but not the changes to metadata. And then we got msync, which is for memory map. And then we got sync. I think fsync is for a file descriptor, if I remember. No, yeah, file descriptors. Looks like. No, file description, which is descriptor, which is 1. So fsync is file descriptor base. If we do man2 sync, that's all sync and syncfs. Huh. Explain the difference between syscalls fsync and sync, because they all take file descriptors. I know what datasync does, and okay, so syncfs. Okay, so this syncs everything. This syncs a file system, specifically the file system that file descriptor is using. And then fsync is like literally syncing the file itself, the inodes of the file itself. And then fdatasync is just the data, not the metadata of the file. Okay, that makes sense. So I had to revisit that. And then we got M-sync. So any other types of syncing in the syscall table? Sync file range. That seems very similar to fsync or fdatasync. Oh, but fdatasync you can't give a range. That's what it is. Okay. It's a bit of a unclean API. The naming is a bit unclear. The remaining arguments FD and offset are used with file mappings. They are ignored for anonymous mappings. The FD argument is a file descriptor identifying the file to be mapped. The offset argument specifies the starting position of the mapping file in the file. It must be a multiple of system page size. To map the entire file, we specify offset as 0 and length as the size of the file. Say more about file mappings in section 49.4. Memory protection in more detail. As noted above, the mmap prot argument specifies the protection on a new memory mapping. It can contain the value prot none or a mass of one of the more of the flags prot read, prot write, and prot exec. If a process attempts to access a memory region in a way that violates the protection on the region, then the kernel delivers SIGSEG-V signal to a process. So you can get a SIGSEG-V for a protection violation. Which is, I wonder if that's the reason why you get a SIGSEG-V when you read memory that's like not in a map. Because that memory is just like automatically, you can't read, you can't write, you can't exec. There's no access to those regions. Although SIGSEG-V specifies that SIGSEG-V should be used to signal memory protection violations, on some implementation, SIG-bus is used instead. One of the pages of memory marked prot none is as guard pages. So you can't read, you can't write, and you can't exec it. So guard pages at the start or end of a region of memory that a process has allocated. If the process accidentally steps into one of the pages marked prot none, the kernel informs it of the fact by generating SIGSEG-V. Okay, so it's like a little boundary. It's like, okay, I don't want you to like, like if you're reading data off the end of an array, and you don't want that to potentially, I mean, obviously, like you don't want that to ever happen usually. But if you are doing that, say there's an exploit on your program, you want that program to hit a SIGSEG-V instead of continuing to read memory into like a different map or a region that is being used for something that could be sensitive. Memory protections reside in process private virtual memory tables. Process private virtual memory tables. Those different processes may map the same memory region with different protections. Memory protection can be changed using the mprotect system call. On some Unix implementations, the actual protections placed on the pages of a mapping may not be exactly those specified in prot. In particular, limitations of the protection granularity of the underlying hardware, e.g. older x86-32 architectures, mean that on many Unix implementations, prot read implies prot exec and vice versa. And in some implementations, specifying prot write implies prot read. However, applications should not rely on such behavior. Prot should always specify exactly the memory protections that are required. Modern x86-32 architecture provides hardware support for marking pages page tables as NX, no execute. And since kernel 268 Linux makes use of this feature to properly separate prot read and prot exec permissions on Linux x86-32. Alignment restrictions specified in standards for offset and adder. SUSE3 specifies that the offset argument of mmap must be page aligned, and that the adder argument must also be page aligned if map fixed is specified. Okay. I don't know why in the morning I get really bad congestion. I like sneeze a lot. I get the sniffles. It seems to happen like every single day. But it's like only when I start the stream. Okay. So it's saying that the offset and the adder are supposed to be page aligned. Linux conforms to these requirements. However, it was later noted that the SUSE3 requirement differed from earlier standards which imposed looser requirements on these arguments. The consequence of SUSE3 wording was to unnecessarily render some formally standards conform and implementations non-conforming. SUSE4 returns to the looser requirements. An implementation may require that offset be a multiple of system page size if map fix is specified. Then an implementation may require that adder be page aligned if map fix is specified. And adder is non-zero, then adder and offset shall have the same remainder modulo the system page size. A similar situation arose for the adder argument of mprotect, msync, and munmap. SUSE3 specifies that this argument must be page aligned. SUSE4 says that the implementation may require this argument to be page aligned. Example program. Program 49.1 demonstrates the use of mmap to create a private file mapping. This program is a simple version of cat. It maps the entire file named in its command line argument and then writes the contents of the mapping to standard out. Okay. Let's try implementing that ourselves. And then we can just use the book as reference if we need to. Okay. Jump over to the Linux program interface, zoom in a little bit. So in here, mkdir for chapter 49. We're going to want to cp chapter 48 slash makefile and .git ignore into chapter 49, cd in there, and then here I'm going to say vim cat.c, and we'll have our main. It's going to take in an arg v 1. That's going to be our char star for our path. And then we're going to assert that we have argc of will be 2. We're going to need to pound include some things up here. We're going to say assert.h and standard lib, and what else? Well, we'll come to that. So now that we got our args, we're going to do our mmap, and I'm just going to load up my man2 mmap sysmman. I wonder why they call it sysmman. That seems weird. Sysmman.h, and then here we're going to say, hey, we're going to mmap We need to find out the size. Find out the size of the file, because it could be possible that it's too big. If file is above, what would you say? The file could easily be above the limits, the memory of the system. Note. Okay, but we're gonna pass in here. How do we find the length of a file? How do you find the length? Oh, use stat, obviously. So we're gonna say, hey, stat of, we'll do man to stat. It's gonna require sysstat up here. Here we're gonna say, hey, I'm gonna stat the path, and I'll give you some data here. So stat buff is going to be a struct stat pointer. No, struct stat, and then we give it a pointer here, stat buff. Okay, and that's going to give us back a int result. We'll just say if that is less than 0, then we got a problem, and we'll just p-error out the stat and return error failure. We'll say exit failure. There we go. And p-error, I think we need something called standard IO. Yeah. Okay, so now that we got our mmap, or got our stat, we can get our length, which is going to be stat buff. We don't have to dereference it. And then we get length, block size. What do we got here? We got to have the length in the stat. Len. Size. So it'd be st size. So stat buff dot st size. And then all right, what's the next argument here? We don't need this thing. This, all right. So we got our length. The adder, we're happy with null. Wait a minute. Why do we have size twice there? Oh, okay. I got these reversed. So this is like a short form, which is just, you just give it the length that you want to memory map. We got other plans here. So the prot will be read write, which is, what are the constants here? Prot read, and we're not going to write it. We're not going to exec it, so we just say read. The flags here, what were these used for again? Oh, this is going to be if it's private or shared. You can just say private, map, private, and then what's the next thing? The file descriptor, we'll just say FD, and the offset will be 0. Okay, so we need to open the file. We statted it, now we need to open it to get the FD. So we say man to open, and we're going to open path. O read only. Can't say O read only. What are the freaking flags here? Flags. We don't want to create it, do we? We'll say no on the create. Yeah, because it's cat. Cat's not going to create a file. It's going to be read only. But I don't know how to do the read only. Which should be where? We'll say read. Here it is. RD only. RD only. Wonder why that didn't pop up there. Do I need a special? Oh, that's right. I don't have the header. That's why. So I need FCNTL. Now I get the completion there. Okay, great. So we have our path, our flags. The mode can be 0, or it can be left off because I don't need it. That gives us back our FD, which you can say int here. And then we say if FD is less than 0, then we just PR out our open and return exit failure. Okay, so that takes care of that. This we should be able to get back our adder, which is now, oops, sorry, buffer delete that. Man to mmap. It's a void star, so we can cast this thing to be a char star. I don't want it to be a void star. And then adder will be a char star. Adder. Cool. So you're pointing at a character, and we have the size in our stat buff. So now, now we need to read all the bytes, writing them to output, standard out, std out. Okay, so we go into for loop, some condition that I don't know yet. We want to perform our read. Man to read. Read is going to be size of the buffer. It's going to give us back the size that it actually read. So let's allocate a buffer here. I think there's a way. There is a send to, where you can send a file to another file descriptor. Yeah, a socket. It's not a file descriptor though. I thought there was like a. Is there a syscall similar to send to where you can hand the, I mean, this won't be applicable in our situation because we're using memory mapping, but I'm kind of curious. Is there a syscall similar to send to where you can hand the kernel to file descriptors and let it do the IO to read from one and write to the other without context switching. Send file. So send to, that's for a socket. I meant send file. There it is. That's cool. I like send file. For some reason I thought it was send to. It's been a while since I've used it. Alright, so we need to man to read. We're going to allocate our buffer. So do we want to use heap memory for this? We can use stack memory. So we say buff is a char star, which we can get by saying it's an array, and the size of it will be 1 bit shift over to 20, which would be about a meg, I think. Python 1 bit shift over 20. It's about a meg, yeah. Okay. So now we have a meg buffer. We're gonna read. So I need to get my man to read back up here. Read the FD. Sorry, no. Actually, we don't need our buffer because we're reading directly from the memory mapped area. We're going to do a write. We're not going to do any reads. I don't know why I'm even in read. We're simply going to write the standard out to the FD. No, to standard out. Standard out, which will be file no. Is it file no? Standard out. Standard out. File no. I thought it was file no. File. Can I go to definition on that? No. What is the C standard out file FD constant? Standard out file no. Okay. Standard out file no. I can't go to definition on that because why? Man to write. Where would this thing be defined at? What header is in Unix standard.h? Okay. Unix standard.h. Alright, now that we got our file now, which is only just one, we could have just typed in one there. Just nice to have the fancy names for it. Okay, so we have file descriptor. Our buffer is going to be adder, and the size. So we have the size here. I'm going to copy that size. I'm just call it size. And we'll say integer size, or it should be like a size t maybe. Size is equal to that. It's an off t. Okay, off t. So you have our size. So forever we're going to say, hey, go up to size. Yeah. I mean, we could do a single write call, but chances are the write's going to return with written. So we say written. Or I just say n. N is easier. Size t. S size t n. So now we can say, why is this an offset and not a S size T? So we're going to do a write, and if n, well, basically we're going to say like size is now minus equal to n, and then if size is greater than 0, then we continue, else we break. So our condition here should always be size is greater than 0. So while size is greater than 0. And then here we should do an error check. We say if n is less than 0, then, well, what if it is 0? On success, the error number, on error is -1. What about 0? 0. If count is 0, FD refers to regular file, then write may return a failure. The count is 0. Okay. Doesn't say anything about the return value being 0. So we'll just say if n is less than 1, then we p error out the write and return exit failure. Otherwise, you subtract off there, and at the end we just return there. Okay, let's try making that, and then we build cat Etsy services. Hey, look at that, it works. And I'm gonna redirect that to temp foo, and we can do a delta on temp foo and Etsy services. There's no delta. It works. I wrote it myself. Cat.c. Let's see what they did. See, he's really a big fan of like doing the variable declarations up at the top of the function. I like doing them where they're used. It's like you don't really care about the FD until you're actually opening it, you know? And I'm pretty sure the compiler is smart enough to like compute the stack size for these things. It's not like you need to have it up there. So that's one thing that's different in our code. He does a usage thing, which is nice to have, obviously. I'm too lazy for that. I just assert things. Then he doesn't do the stat, interestingly. But he does open. He does an fstat. What is fstat? Why is that different than stat? Did I use the wrong one? Man stat versus fstat? No. Fstat you give it the file descriptor. Okay, so his is better because I didn't realize that I needed to open it, so I statted it first to get the length, and then later I opened it, and then I forgot that it would be better to do the fstat. So let's do the fstat here, and we'll give it the fd and the struct, and I think that should be good. Okay, let's go ahead and make it again, and we'll do our test again, where we do that, and then we do our delta. Yep, okay, everything's good. So that's an improvement. And then let's check out his memory mapping versus mine. Cat, let's see. So here, he did an fstat into the memory he already allocated, so I like mine better there. And then he's doing these like error exits, which makes it easier to read, I guess, but I would rather not have a dependency on a separate library that he wrote. Okay, so we get past the stat, and we go into our memory map. null size. He passes in the size directly. He doesn't retry, so I think mine's better than his in that regard, because I copy the size to stack space and then I decrement it. So if the write was interrupted, I guess we should handle that case, E interrupted. But yeah, I mean, you get the general idea. It's not. Let's handle the interrupted case. It's gonna annoy me. Man to stat, man to right. Enter. E enter. Yeah, E enter. So we say if n is equal to E enter, then we're just gonna continue. I don't really like these like things without the curly braces, not my style. And then I need this E enter thing. C or error node.h. Okay, that makes sense. Error node.h. Wait a minute. E again, file descriptor refers to a file other than a socket that has been marked non-blocking. And the right, so we're not marked as non-blocking. I just wanted to handle E enter because that's something that is in my head now permanently, that any syscall pretty much you have no guarantees of it not being interrupted by the kernel and just giving you an E interrupted. Let me block this spammer here. Please stop spamming. It's annoying. All right. So there's a little bit of a detour there, but it is nice to get some exercise writing some programs. I did want to come back and read this at some point. Oops, there we go. All right, unmapped and mapped region, M unmap. The M unmap system call performs the converse of mmap, removing a mapping from the calling process virtual address space. The adder argument is the starting address of the address range to be unmapped. It must be aligned to a page boundary. Substitute 3 specifies that adder must be page aligned. Substitute 4 says that implementation may require this argument to be page aligned. The length argument is a non-negative integer specifying the size in bytes of the region to be unmapped. The address range up to the next multiple of the system page size will be unmapped. Commonly, we unmap an entire mapping. Thus, we specify adder as the address returned by the previous call to mmap and specify the same length value that was used in the mmap call. Here's an example. So we do the mmap with a bunch of stuff. And we do unmap with the same adder and same length. Alternatively, we can unmap part of a mapping. That's pretty cool. That's pretty cool. Gonna highlight that. In which case, the mapping either shrinks or is cut in two, depending on where the unmapping occurs. Sorry, I'm like offset here. Mapping occurs. It's also possible to specify an address range spanning several mappings, in which case all of the mappings are unmapped. They have to be next to each other though. If there are no mappings in the address range specified by adder and length, then munmap has no effect and returns 0 for success. Oh, okay. So you can just do a huge range even though there's no mappings there. During unmapping, the kernel removes any memory locks that process holds for a specified address range. Memory locks are established using mlock or mlockall as described in chapter 50. All the process's mappings are automatically unmapped when it terminates or performs an exec. Okay, makes sense. To ensure that the contents of a shared file mapping are written to the underlying file, a call to msync should be made before unmapping of mapping with munmap. Okay, sounds reasonable. Figure it would do it for you though, because like, why would you want to unmap a area memory and not sync out the changes to it if it's a file mapping? File mappings. To create a file mapping, we perform the following steps. Obtain the descriptor of the file, typically via call to open. We've already done this with the cat file. Pass that file descriptor as a FD argument to the call to mmap. As a result of these steps, mmap maps the content of the open file to the address space of the calling process. Once mmap has been called, we can close the file descriptor without affecting the mapping. However, in some cases, it may be useful to keep the file descriptor open. See, for example, listing 49.1 and also chapter 54. As well as normal disk files, it is possible to use mmap to map the contents of various real and virtual devices, such as hard disk, optical disks, and debmem. That's pretty cool. That's pretty cool. It is. Pretty cool. I can imagine that being useful if, like, say you wanted to, like, write out the boot sector of a MBR hard drive, just as an example that pops to mind. You could just memory map the device into your process's address space, do the memory operations to set up that boot sector, flush it with msync, and then map it, and it's done. And you don't have to do any I/O. Whereas with a traditional model, you'd have to first open the device file descriptor, which you also have to do if you're using mmap, but then you'd have to seek to 0 offset or the sector that you want, which isn't a huge problem, but it's another syscall. And then you'd have to do your write operations to write the data out. It's like you're already setting it up in your process memory, and then you have to call these writes to then write the whole thing out to the disk, versus just memory mapping in, setting it up in memory, calling msync, and you're done with it. It seems much more efficient to do it that way, because you're not actually writing stuff to memory, you're writing stuff directly to the disk. The problem being, though, is that, like, if you write it to into a temporary region of memory and then write it all out to disk, everything leading up to that write is temporary and you can back out of it. Whereas if you're doing your writes directly to the disk and they get interrupted halfway, you have like a torn write that's like invalid state. You could like mess things up. So depends on the use case. I'm gonna go take a bio break real quick. I'll be right back. Alrighty. Where do I leave off here? I think it was on file mappings, right? As a result of these steps, mmap maps the contents of the open file to the address space in the calling process. Once mmap has been called, we can close the file descriptor. Yeah, we talked about that. As well as normal disk files. Yeah, we talked about that. The file referred to by the descriptor fd must be opened with permissions appropriate to the value specified in prot and flags. In particular, the file must always be open for reading, and if prot, write, and map shared are specified in the flags, then this file must be open for both reading and writing. The offset argument specifies the start byte of the region to be mapped from the file and must be a multiple of system page size. Specifying offset as 0 causes the file to be mapped from the beginning. The length argument specifies the number of bytes to be mapped. Together, the offset and length argument determine which region of the file is to be mapped into memory, as shown in figure 49.1. It is weird that it has to be page size aligned. I guess that's just kind of how things are implemented. On Linux, the pages of a file mapping are mapped in on the first access. This means that if changes are made to a file region after mmap call, but before a corresponding part, i.e. page of the mapping is accessed, then the changes may be visible to the process if the page has not otherwise already been loaded into memory. This behavior is implementation dependent. Portable applications should avoid relying on particular kernel behavior in this scenario. Private file mappings. The two most common use of private file mappings are to allow multiple processes to execute the same program, or using the same shared library, or share the same read-only text segment, which is mapped from the corresponding part of the underlying executable or library file. Although the executable text segment is normally protected to allow only read and execute access, part read and part exec, it is mapped using map private rather than map shared because a debugger or a self-modifying program can modify the program text after first changing the protection on the memory. I've done that before. And such changes should not be carried through to the underlying file or affect other processes. I have done that before. Self-modifying code. And I guess debuggers too, because debuggers insert trap instructions and stuff. To map the initialized data segment of an executable or shared library, such mappings are made private so that the modifications to the contents of the mapped data segment are not carried through to the underlying file. Both of these uses of nmap are normally invisible to a program because these mappings are created by the program loader and dynamic linker. Examples of both kinds of mapping can be seen in the procpid maps output shown in section 48.5. Other less frequent uses of private file mapping is to simplify the file input logic of a program. It is similar to the use of the shared mapping or memory mapped I/O described in the next section, but allows only for file input. Alrighty. Shared file mappings. Well, we get a couple diagrams. Or we already looked at that one. We got program, some other stuff here, anonymous mappings, remapping a map region, nonlinear mappings. Okay. So 25 to 44. So we got about 20 pages left, roughly. 18 pages for another hour. Put us at about 12:30, which will be around lunchtime for me. So I think we can finish this by lunch. I am enjoying reading this and stopping to, play with the, write our own cat program, play with some of the memory mapping stuff. Shared file mappings. When multiple processes create shared mappings of the same file region, they share the same physical pages of memory. In addition, modifications to the contents of the mapping are carried through the file. In effect, the file is being treated as the paging store for this region of memory. As shown in figure 49.2, we simplify things in this diagram by omitting to show that the map pages are typically not contiguous in physical memory. Shared mappings serve two purposes: memory mapped I/O and IPC. We consider each of these uses below. I think the IPC is like only between parent and child. I don't think IPC works with just basic memory mapping. I think you need the POSIX shared memory stuff if you want to do it without a backing file. So we got two processes with a shared mapping of the same region of the file. Memory mapped I/O. Since the contents of the shared file mapping are initialized from a file, and any modifications to the contents of the mapping are automatically carried through to the file, we can perform file I/O simply by accessing bytes of memory, relying on the kernel to ensure that the changes to memory are propagated to the map file. Typically, a program would define a structured data type that corresponds to the contents of the disk file, and then use that data type to cast the contents of the mapping. This technique is referred to as memory mapped I/O and is an alternative to using read and write to access the contents of a file. All right. Memory mapped I/O has two potential advantages. By replacing read and write system calls with memory access, it can simplify the logic of some applications. And I imagine also increase performance because doing loads and stores onto memory seems to be, in my mind, faster than doing all the context switching in and out of the kernel for the reads and writes. It can, in some circumstances, provide better performance than file I/O carried out using the conventional I/O system calls. The reason that memory mapped I/O can perform performance benefits are as follows. A normal read and write involves two transfers, one between the file and the kernel buffer cache, and the other between the buffer cache and user space buffer. Using mmap eliminates the second of these transfers. For input, the data is available to the user process as soon as the kernel has mapped the corresponding file blocks into memory. For output, the user process merely needs to modify the contents of the memory. Let me reread that. All right. Sorry about that. I should have muted. All right. A normal read or write involves two transfers, one between the file and the kernel buffer cache, and the other between the buffer cache and the user space buffer. Using mmap eliminates the second of these transfers, yes. For input, the data is available to the user process as soon as the kernel has mapped the corresponding file blocks into memory. For output, the user process merely needs to modify the contents of the memory and can then rely on the kernel memory manager to automatically update the underlying file. In addition to saving a transfer between kernel space and user space, mmap also can improve performance by lowering memory requirements. When using read and write, the data is maintained in two buffers, one in user space and the other in kernel space. When using mmap, a single buffer is shared between the kernel space and user space. Furthermore, if multiple processes are performing I/O on the same file, then using mmap, they can all share the same kernel buffer, resulting in additional memory saving. Performance benefits from memory mapped I/O are not likely to be realized when performing repeated random access in a large file. If we are performing sequential access of a file, then mmap will probably provide little or no gain over read and write. Assuming that we perform I/O using buffer sizes big enough to avoid making a large number of I/O system calls. The reason that there is little performance benefit is that regardless of which technique we use, the entire contents of the file will be transferred between disk and memory exactly once, and the efficiency gains of eliminating a data transfer between user space and kernel space and reducing memory usage are typically negligible compared to the time required for disk I/O. Memory mapped I/O can also have disadvantages. For small I/Os, the cost of memory mapped I/O, e.g. mapping, page faulting, unmapping, and updating the hardware memory management unit's translation look-aside buffer can actually be higher than for simple read and write. In addition, it can sometimes be difficult for the kernel to efficiently handle write-back for writable mappings using the msync or sync file range. Use the msync or sync file range can help improve efficiency in this case. IPC using a shared file mapping. Since all processes with a shared mapping of the same file region share the same physical pages of memory, the second use of the shared file mapping is as a method of fast IPC. The feature that distinguishes this type of shared memory region from System V's shared memory object is that modifications to the contents of the region are carried through to the underlying map file. This feature is useful in an application that requires that shared memory contents to persist across applications or system restarts. Example program listing 49.2 provides a simple example of the use of mmap to create a shared file mapping. This program begins by mapping the file named in the first command line argument and then prints the value of the string lying at the start of the map region. Finally, if a second command line argument is supplied, that string is copied into the shared memory region. The following shell session log demonstrates the use of this program. We begin by creating a 1024 byte file that's populated with zeros. Yep. Looks good to me. Sorry, I was on the wrong page here. So we just ran this command here, dd input file dev 0, output file s.txt, byte is 1, count is 1024. We then use our program to map the file and copy a string into the mapped region. Just say, hey, I map the file and copy in hello. The program displays nothing for the current string because the initial value of the mapped files began with a null byte. Next, we use the program again to map the file and copy a new string into the mapped region. Yep. Finally, we dump the contents of the file. It says goodbye. A trivial program doesn't use any mechanism to synchronize access by multiple processes to the map file. However, real-world applications typically need to synchronize access to shared mappings. This can be done using a variety of techniques, including semaphores. Let me reread that. My mind was wandering there. Our trivial example doesn't use any mechanism to synchronize access to multiple processes to the map file. However, real-world applications typically need to synchronize access to shared mappings. This can be done using a variety of techniques, including semaphores and file walking. We explained the msync system call in listing 49.2 in section 49.5. So I don't really need to read the source code. I'm pretty sure I understand what's going on there. Boundary cases. In many cases, the size of a mapping is a multiple of the system page size. And the mapping falls entirely within the bounds of the map file. However, this is not necessarily so, and we now look at what happens when these conditions don't hold. Figure 49.3 portrays the case where the mappings fall entirely within the bounds of the map file, but the size of the region is not a multiple of system page size, which we assume is 4096 bytes for the purpose of this discussion. So we mmap in. Hold on, let me go back to my prototype for mmap. Oops. So mmap in. The address is going to be 0. That's fine. Our length is 6,000. Then we have prot m shared fd 0. Okay. That makes sense. So we have our byte offset up to 6,000 is the requested size of mapping, remainder of the page. Because we need two 4096s, that's 8,200 something. Yeah, that value right there. So this is just a dead space here. This is actual mapped region of the file. Yeah, I mean that makes sense. So this is going to be dead space here. Oh, do they actually map in the bytes of the file, even if it's not requested? That's kind of jank. Hopefully that's not the case. Since the size of the mapping is not a multiple system page size, it is rounded up to the next multiple system page size. Because the file is larger than the rounded up size, the corresponding bytes of the file are mapped as shown. That's weird. Attempts to access bytes beyond the end of the mapping result in generation of sig-seg-v signal. Assuming that there's no other mapping in this location, the default action for the signal is determined to process with a core dump. When the mapping extends beyond the end of the underlying file, see figure 49.4. Let's look at that figure here. So in this case, we have 8192 bytes that we want to map in from 0, but the file isn't that big. So we go all the way to 49.6. Then we get zeros here. Accessible, map to file. Accessible, not map to file. Sig-seg bus on the rest of this area. What if someone comes in and starts like monkeying with the file though, and like truncates it out to this length? Will these now be accessible? I wonder. When mapping extends beyond the end of the underlying file, the situation is more complex. As before, because the size of the mapping is not a multiple of a system page size rounded up, however, in this case, while the bytes of the rounded up region are accessible, they are not mapped to the underlying file since no corresponding bytes exist in the file. Instead, they are initialized to 0. Substitute 3 requires this. These bytes will nevertheless be shared with other process mapping of the file if they specify a sufficiently large length argument. Changes to the bytes are not written to the file. Ah, interesting. But what if the changes to file, do they show up in the mapping? If the mapping includes pages beyond the rounded up region, like bytes of 49.6 and beyond, in figure 49.4, then attempts to access addresses in the pages results in generation of sig-bus signal, which warns the process that there is no region of the file corresponding to these addresses. As before, attempts to access addresses beyond the end of the mapping result in a generation of sig-seg-v signal. From the above description, it may appear pointless to create mappings whose size exceeds the underlying file. However, by extending the size of the file, using ftruncate or write, we can render previously inaccessible parts of such mapping usable. That's what I was wondering about. That's pretty cool. Memory protection and file access mode interactions. The thing I like about this author is like you'll have these like questions and then he'll just answer your question because it's so thorough. Like he's kind of like thought about all these different situations. He presents them to you, and then he shows you all the edge cases, and then you're thinking, oh, what about this? And he's like, oh, I got that right here. And then the diagrams. I especially love it when he has diagrams. There's not a lot of diagrams in the book, but the ones that he does have really hit home. High quality. Memory protection and file access mode interactions. One point that we have not so far explained in detail is interaction between memory protection specified in mmap prot argument and the mode in which the map file is opened. I thought we already discussed that. As a general principle, we can say that the prot read and prot exec protections require that map file is opened with read only or read write, and that the prot write protection requires that the map file is open write only or read write. Yeah. However, the situation is complicated by the limited granularity of memory protections provided by some hardware architectures. For such architectures, we make the following observations. all combinations of memory protection are compatible with opening the file with the open read-write flag. No combinations of memory protections, not even just prot write, is compatible with file opening write only. This error e-access results. The error, okay. This is consistent with the fact that some hardware architectures don't allow us write only access to a page. As known in section 49.2, prot write implies prot read on those architectures, which means that if a page can be written, then it can also be read. The read operation is incompatible with write only, which must not reveal the original contents of the file. The results when a file is open with the read-only flag depend on whether we specify map private or map shared when calling mmap. For a map private mapping, we can specify any combination of memory protection in mmap because modifications to the contents of a map private page are never written to the file. The inability to write to the file is not a problem. For a map shared mapping, the only memory protections that are compatible with read-only are prot read and prot read exec. This is logical since a prot write map shared mapping allows updates to the map file. Synchronizing a mapped region, msync. The kernel automatically carries modifications of the contents of a map shared mapping through to the underlying file, but by default provides no guarantees about when such synchronization will occur. Subset 3 doesn't require an implementation to provide such guarantees. The msync system call gives an application explicit control over when a shared mapping is synchronized with the mapped file. Synchronizing a mapping with the underlying file is useful in various scenarios. For example, to ensure data integrity, a database application may call msync to force data to be written to disk. Calling msync also allows an application to ensure that updates to a writable mapping are visible to some other process that performs reads on the file. The adder and length argument to msync specify the starting address and size of the memory region to be synchronized. So you say msync, this adder, this length, and some flags. The address specifies adder must be a page aligned, and length must be rounded up to the next multiple of page size. Subset 3 specifies that adder must be pre-aligned. Subset 4 says that the implementation may require this to be page aligned. Sorry, it must be page aligned. Okay. Possible values of the flags argument include one of the following. So you can have ms sync and ms async. ms is for memory sync, msync. Perform a synchronous file write. The call blocks until all modified pages of the memory region have been written to disk. Async, perform an asynchronous file write. The modified pages of memory region are written to the disk at some later point and are immediately made visible to other processes performing a read on the corresponding file region. Another way to distinguish those two values is to say that after an ms sync operation, the memory region is synchronized with disk, while after an ms async operation, the memory region is merely synchronized with the kernel buffer cache. If we take no further action, an ms async operation, then the modified pages in the memory region will eventually be flushed as part of the automatic buffer flushing performed by the pd flush kernel thread. KU updated in Linux 2.4 and earlier. So pd flush. Do I have pd flush? Let's see. ps aux grep for pd flush. Nope. Do I have anything for flush? I got kworker. It's called kworker flush btrfs flush deallocate kdbm flush. These are all flushing things in the kernel. Okay. On Linux, there are two non-standard methods for initializing the output sooner. We can follow the call to msync with a call to fsync or fdatasync on the file descriptor corresponding to the mapping. This call will block until the buffer cache is synchronized with the disk. Alternatively, we can initiate asynchronous write out to the pages using the POSIX fadvise operation. The only specific details in these two cases are not specified in SUSV3. On the other hand, one other value can additionally be specified in flags, which is ms invalidate. Invalidate cached copies of map data. After any modified pages in the memory region have been synchronized with the file, all pages of the memory region that are inconsistent with the underlying file data are marked as invalid. When next referenced, the contents of the pages will be copied from the corresponding locations of the file. As a consequence, any updates that have been made to the file by another process are made visible to the memory region. Like many other modern Unix implementations, Linux provides a so-called unified virtual memory system. This means that where possible, memory mappings and blocks of the buffer cache share the same pages of physical memory. Thus, the views of a file obtained via a mapping and via I/O system calls, read, write, and so on, are always consistent. And the only use of msync is to force the contents of a map region to be flushed to disk. However, a unified virtual memory system is not required by SUSV3 and is not employed on all Unix implementations. On such systems, a call to msync is required to make changes to the contents of the mapping visible to other processes that read the file. And the ms invalidate flag is required to perform the converse action of making writes to the file by another process visible to the map region. Multi-process applications that employ both mmap and I/O system calls to operate on the same file should be designed to make appropriate use of msync if they are to be portable to systems that don't have a unified virtual memory system. Boom, 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 boom. So we've got additional mmap flags, additional anonymous mappings, remapping a mapped region, map no reserve and swap space overcommit, the killer. It's the first time encountering the killer. Map fixed flag, nonlinear mappings, and a summary. Okay. In addition to map private and map shared, Linux allows a number of other values to be included in the mmap flags argument. Table 49 summarizes these values. Other than map private and map shared, only the map fixed flag is specified in SUSV3. So quite a few different things. So we have anonymous to create anonymous mapping, fixed to interpret address argument exactly instead of rounding it to the page, or the next page alignment. Lock map pages into memory. Huge table, create a mapping that uses huge pages. No reserve, control reservation of swap space. Private, modifications to map data are private. Populate the pages of a mapping. Shared, modifications to mapping are visible to other processes and are propagated to underlying file. Uninitialized, don't clear, and anonymous mapping. Okay. The following list provides further details on the flags value listed in table 49.3, other than private and shared, which have already been discussed. Okay. Anonymous. Create an anonymous mapping. This is a mapping that is not backed by a file. We describe this flag further in section 49.7. Fixed. 49.7, which will be in this chapter. Okay, fixed. We describe this flag in section 49.10. Huge table. This flag serves the same purpose for mmap as the huge table flag serves for system V shared memory segments. Locked. Preload and lock the map pages into memory in the manner of mlock. We describe the privilege required to use this flag and the limits governing its operation, section 52. No reserve. This flag is used to control whether reservation of swap space for a mapping is performed in advance. Okay. Populate the pages of a mapping. For a file mapping, this will perform read ahead on the file. This means that later access of the contents of the mapping won't be blocked by page faults, assuming that memory pressure is not in the meantime cause the pages to be swapped out. Map uninitialized. Specifying this flag prevents the pages of an anonymous mapping from being zeroed. It provides a performance benefit but carries a security risk because the allocated pages may contain sensitive information left by a previous process. This flag is thus only intended for use on embedded systems where performance may be critical and the entire system is under the control of the embedded application. This flag is only honored if the kernel is configured with the config mmap allow uninitialized option. Anonymous mappings. Anonymous mapping is one that doesn't have a corresponding file. I thought we already talked about this as a non-shared in the beginning of the chapter, but I might have been confused. So a private, they did mention anonymous. Okay. We didn't talk much about it early on, but we did mention it. An anonymous mapping is one that doesn't have a corresponding file. In this section, we show how to create anonymous mappings and look at the purposes served by private and shared anonymous mappings. So map anonymous and dev0. In Linux, there are two different equivalent methods of creating anonymous mapping with mmap. Specify map anonymous in flags and specify fd as -1. On Linux, the value of fd is ignored when map anonymous is specified. However, some Unix implementations require fd to be -1 employ map anonymous, and portable applications should ensure they do this. We must defer either to BSD source or SVID source feature test macros to get the definition of map anonymous from mman.h. Linux provides constant map anon as a synonym for map anonymous for compatibility with the other Unix implementations using this alternative name. Open the dev0 device file and pass the resulting file descriptor to mmap. Dev0 is a virtual device that always returns 0 when read from it. Writes to this device are always discarded. Common use of dev0 is to populate a file with zeros using the dd command. So if you map that in, it'll be unshared by default because even if you wrote to it, it's just going to throw away the writes. So it's going to be private by default. It's going to be private anonymous mapping. If we go back to our table, I guess it would be shared. It could be shared too because it could be shared, but it's not going to write its data out to a file. It's going to share with other processes. With both the map anonymous and dev0 techniques, the bytes of the resulting map are initialized to 0. For both techniques, the offset argument is ignored since there is no underlying file to which to specify an offset. We show examples of each technique shortly. The map anonymous and dev0 techniques are not specified in SUSV3, although most Unix implementations support one or both of them. The reason for the existence of two different techniques with the same semantics is that one, map anonymous, derives from BSD, while the other, dev0, derives from System V. Map private. Anonymous mappings. Map private anonymous mappings are used to allocate blocks of process private memory initialized to 0. We can use dev0 technique to create a map private anonymous mapping as follows. So say, hey dev0, I'm going to open you up, and then we're going to do our little dance here. where we don't care where you're going to map it to. Here's a length, and I want to read and write to it. I want it to be private, and the file descriptor for dev0. The GMC implementation of malloc uses map private anonymous mappings to allocate blocks of memory larger than the mmap threshold bytes. This makes it possible to effectively deallocate such blocks via munmap if they are later given to free. It also reduces the possibility of memory fragmentation when repeatedly allocating and deallocating large blocks of memory. Mmap threshold is 120 KB by default, but this parameter is adjustable via mallopt library function. Map shared anonymous mappings. A map shared anonymous mapping allows related processes, e.g. parent and child, to share a region of memory without needing a corresponding map file. Map shared anonymous mappings are available only with Linux 2.4 and later. We can use map anonymous technique to create the map shared anonymous mapping. Yep. In this case, we don't have to do the open on dev0. We didn't have to do it on the previous one either. Just use -1 as its file descriptor and pass in map anonymous. If the above code is followed by a call to fork, then because the child produced by fork inherits the mapping, both processes share their memory region. The program listing 49.3 demonstrates the use of either map anonymous or dev0 to share a mapped region between a parent and child process. The choice of technique is determined by whether use map anon is defined when compiling the program. The parent initializes an integer in the shared region to 1 prior to calling fork. The child then increments the shared integer and exits, while the parent waits for the child to exit, then prints the value of the integer. When we run this program, we see the following output. Yep. Makes sense. And we're just going to use a if def, use map anon. So anonymous mapping, much more terse. You just do a single syscall. The dev0 thing, we have to do an open and pass it in here. Otherwise, it's the same. I'd rather just pass it in here and say map anonymous. Avoid the additional syscall. Additional 2 syscalls because you have to close it as well. Okay, then we go into our fork. We write the value 1, we go into fork, the child then increments that value, it then does its unmap, which it doesn't really need to do. It should probably call _exit here. And then this just waits for the exit code and then calls its unmap. Which I don't think you have to unmap if you're exiting. I think that's handled by the kernel. Remapping your map region. On most Unix implementations, once a mapping has been created, its location and size can't be changed. However, Linux provides the non-portable mremap system call, which permits such changes. So you got an mremap, old address, old size to new address. Sorry, old address, old size, new size, flags. There's no new address. I guess we're just saying, hey, give me back a new address. I don't care where it is. Okay. The old address and old size argument specify the location and size of an existing mapping that we wish to expand or shrink. The address specified by an old address must be page aligned and is normally a value returned by previous call to mmap. The desired new size of the mapping is specified in new size. The values specified in the old size and new size are both rounded up to the next multiple of system page size. By carrying out the remapping, the kernel may relocate the mapping within the process's virtual address space. Whether or not this is permitted is controlled by the flags argument, which is a bit mask that may either be 0 or include the following values. So you can say, hey, may move. If this flag is specified, then as space requirements dictate, the kernel may relocate the mapping with the process virtual address within the process virtual address space. If this flag is not specified, then there's insufficient space to expand the mapping at the current location. Then we get an mem. The flag, fixed. This flag can be used in conjunction with may move. It serves a purpose for m remap that is analogous to that served by mapfix for mmap. This flag is specified, then m remap takes an additional argument, which is the new address, that specifies a page aligned address to which the map should be moved. Any previous mapping in this address range specified by new address and new size is unmapped. On success, m remap returns the starting address of the mapping. Since if the map m remap may move flag is specified, this address may be different from the previous starting address. Pointers to the region may cease to be valid. Therefore, applications that use m remap should only use offsets. To use only offsets, not absolute pointers, when referring to addresses in the mapped region. On Linux, reallocate function uses mmremap to efficiently reallocate large blocks of memory that malloc previously allocated using mmap. We mentioned this feature of the glibc malloc implementation in section 49.7. Using mmremap for this task makes it possible to avoid copying of bytes during the reallocation. Oh, interesting. That is pretty cool. I'm going to highlight that. What that is saying is that like the kernel literally is not making any copies. Like you got this memory and you want to move it over to there, different address range, you just call mmremap and the kernel just updates its bookkeeping, but it's not actually moving electrons around to copy the data. That's cool. Map no reserve and swap space over committing. Okay. Some applications create large, usually private, anonymous mappings, but use only a small part of the map region. For example, certain types of scientific applications allocate a very large array, but operate on only a few widely separated elements of the array, a so-called sparse array. If the kernel allows allocated or reserved enough swap space for the whole such mapping, then a lot of swap space would potentially be wasted. Instead, the kernel can reserve swap space for the pages of the mapping only as they are actually required. This approach is called lazy swap reservation and has the advantage that the total virtual memory used by applications can exceed the total size of RAM plus swap space. To put this another way, lazy swap reservation allows swap space to be overcommitted. This works fine as long as a process doesn't attempt to access the entire range of their mappings. However, if all applications do attempt to access the full range of their mappings, RAM and swap space will be exhausted. In a situation, the kernel reduces memory pressure by killing one or more of the processes in the system. Ideally, the kernel attempts to select the process causing the memory problems. See the discussion on the killer below, but this isn't guaranteed. For this reason, we may choose to prevent lazy swap reservation, instead forcing the system to allocate all of the necessary swap space when the mapping is created. How the kernel handles reservation of swap space is controlled by the use of the map no reserve flag when calling mmap via /proc interfaces that affect the system-wide operation of swap space overcommitting. These factors are summarized in table 49.4. Overcommit memory. Okay. The Linux specific proc sysvm overcommit memory. Let's see what that thing has. Proc sysvm overcommit memory. It's set to 0. The Linux specific overcommit memory file contains an integer value that controls the kernel handling of swap space overcommits. Linux versions before 2.6 differentiate only two values on the file: 0 meaning deny obvious overcommits, subject to the use of the map no reserve flag, and greater than 0 means that overcommits should be permitted in all cases. Denying obvious overcommits means that new mappings whose size doesn't exceed the amount of currently available free memory are permitted. Existing allocations may be overcommitted, since they may not be using all of the pages that they mapped. Since Linux 2.6, a value of 1 has the same meaning as a positive value in earlier kernels, but the value 2 or greater causes strict overcommitting to be employed. In this case, the kernel performs strict accounting on all mmap allocations and limits the system-wide total of all such allocations to be less than or equal to the swap size plus the RAM size times the overcommit ratio. Let's see what our ratio is. 50 kbytes, 0. Okay, great. The overcommit ratio value is an integer expressing a percentage contained in Linux specific overcommit ratio file. The default value contained in this file is 50, meaning that the kernel can overallocate up to 50% of the size of the system's RAM. And this will be successful as long as not all processes try to use their full allocation. Note that overcommit monitoring comes into play only for the following types of mappings: private writable mappings, both file anonymous mappings for which the swap costs of the mapping is equal to the size of the mapping for each process that employs the mapping, and shared anonymous mappings for which the swap cost of the mapping is the size of the mapping, since all processes share that mapping. Reserving swap space for read-only private mapping is unnecessary, since the contents of the mapping can't be modified. There is no need to employ such swap space. Swap space is also not required for shared file mappings, because the map file itself acts as the swap space for the mapping. When a child process inherits a mapping across a fork, it inherits the map no reserve setting for the mapping. The map no reserve flag is not specified in SUSV 3, but it is supported on a few other Unix implementations. In this section, we have discussed how a call to mmap may fail to increase the address space of the process because the system limitations of RAM and swap space. A call to mmap can also fail because it encounters the per process R limit AS, resource limit, described in section 36.3, which places an upper limit on the size of address space of the calling process. The killer. Above, we noted that when we employ lazy swap reservation, memory may become exhausted if applications attempt to employ the entire range of their mappings. In this case, the kernel relieves memory exhaustion by killing processes. The kernel code dedicated to selecting a process to kill when memory is exhausted is commonly known as the out-of-memory killer. The killer tries to choose the best process to kill in order to relieve the memory exhaustion, where best is determined by a range of factors. For example, the more memory a process is consuming, the more likely it will be a candidate for the killer. Other factors that increase the process likelihood of selection are forking too many child processes and having a low priority, i.e. a nice value that is greater than 0. The kernel disfavors killing the following: processes that are privileged, since they are probably performing important tasks; processes that are performing raw device access, since killing them may leave the device in an unusable state; and processes that have been running for a long time or have consumed a lot of CPU, since killing them will result in a lot of lost work. To kill the selected process, the killer delivers the kill signal. That means it just goes away without any notification. The Linux-specific procpid score file, available since kernel 2.6.11, shows the weighting that the kernel gives to a process if it is necessary to invoke the killer. The greater the value of the file, the more likely a process is to be selected, if necessary, by the killer. The Linux-specific procpid adjacent file, also available since kernel 2.6.11, can be used to influence the score of a process. This file can be set to any value in a range between -16 and +15, where negative values decrease the score and positive values increase it. Special value -16 removes the process altogether as a candidate for selection by the killer. For further details, see the proc 5 manual page. The map fix flag. Alright, so we got 1, 2, 3, 4 pages left. So we'll break early here. The map fix flag, specifying map fix and the mmap flags argument, forces the kernel to interpret the address in adder exactly, rather than make it as a hint. If we specify map fix, adder must be page aligned. Generally, a portable application should omit the use of map fix and specify adder as null, which allows the system to choose the address at which to place the mapping. The reason for this are the same as those we outlined in section 48.3 when explaining why it is usually preferable to specify the shared memory adder as null when attaching a system v shared memory segment using shm at attach. There is, however, one situation where a portable application might use map fix if map fix is specified when calling mmap and the memory region beginning at adder and running for length bytes overlaps the pages of any previous mapping. Then the overlapping pages are replaced by the new mapping. We can use this feature to portably map multiple parts of a file or files into contiguous regions of memory as follows. Use mmap to create an anonymous mapping. In the mmap call, we specify adder as null and don't specify the map fix. This allows the kernel to choose the address for mapping. Use a series of mmap calls specifying map fix to map, i.e. overlay file regions into different parts of the mapping created using the preceding step. Although we could skip the first step and use a series of mmap map fixed operations to create a set of contiguous mappings at the address range selected by the application, this approach is less portable than performing both steps, because you might run into a segment that's already been mapped to something else that's not your anonymous mapping. As noted above, a portable application should avoid trying to create a new mapping at a fixed address. The first step avoids a portability problem because we let the kernel select a contiguous address range and then create new mappings within that address range. From Linux 2.6 onward, the remap file pages system call, which we describe in the next section, can also be used to achieve the same effect. However, the use of map fixed is more portable than remap file pages, which is Linux specific. Nonlinear mappings, remap file pages. File mappings created with mmap are linear. There's a sequential one-to-one correspondence between the pages of the map file and the pages of the memory region. For most applications, a linear mapping suffices. However, some applications need to create large numbers of nonlinear mappings, mappings where the pages of the file appear in a different order within contiguous memory. We show an example of nonlinear mapping in figure 49.5. Okay, that's the next page. Let's take a look at it. So we got increasing memory address values left to right. We got memory regions, 3 of them. So 0 goes to page 2, 1 goes to 1, 2 goes to page 0 of the file. So we like reverse them. The byte ordering would be kind of weird. It'd be like a sawtooth. Not sure why you would want to do that, but let's continue talking about it. We described one way of creating nonlinear mappings in the previous section, using multiple calls to mmap with mapfix flag. However, this approach doesn't scale well. The problem is that each of these mmap calls creates a separate kernel virtual memory area data structure. Each virtual memory area takes time to set up and consumes some non-swappable kernel memory. Furthermore, the presence of a large number of VMAs can degrade the performance of the virtual memory manager. In particular, the time it taken to process each page fault can significantly increase, where there are tens of thousands of VMAs. This was a problem for some large database management systems that maintain multiple different views in a database file. Each line in the procpid maps file represents one VMA. Which is a virtual memory allocation, virtual memory area. Okay. From kernel 2.6 onward, Linux provides the remap file pages system call to create nonlinear mappings without creating multiple VMAs. We do this as the following. Creating a mapping with mmap. So we do our mmap. Use one or more calls to remap file pages to rearrange the correspondence between the pages of memory and the pages of the file. All that remap file pages is doing is manipulating process page tables. It is possible to use remap file pages to map the same page of a file into multiple locations within the map region. Okay, the signature here is you give it the address and the size and the protection and an offset where you want to swap it with, I guess, or remap it to. The page off and size arguments identify a file region whose position in memory is to be changed. The pg off argument specifies the start of the file region and units of system page size as returned by sysconf sc page size. This thing like rarely works for me. That's unrecognized. That's 49.6 4K. Okay. The size argument specifies the length. Let me close out of this. Size argument specifies the length of the file region in bytes. The adder argument serves two purposes. It identifies the existing mapping whose pages we want to rearrange. In other words, the adder must be an address that falls somewhere within the region that was previously mapped with mmap. It specifies a memory address at which the file pages identified by PG offset and size are to be located. Both adder and size should be specified as multiples of the system page size. If they are not, then they are rounded down to the nearest multiple of page size. Suppose that we use the following call to mmap to map 3 pages of the open file referred to by the descriptor fd, and that call assigns the returned address 0x4001A000 to adder. Okay, so we say sysconf page size. Now I got my page size. I can then do my mmap 3 times the page size. Okay. The following calls would then create the nonlinear mapping shown in figure 49.5. We then call remap files on the adder that was returned from mmap. We give it our page size, and then which is like the size, and then offset 2. Maps page 2 of the file onto page 0 of the region. So then we give it adder plus 2 times PS, which will take us to the 3rd place, and then we give the size, and we give the offset. Okay. Yeah, that works. There are 2 other arguments of remap file pages that we haven't yet described. The prot argument is ignored and must be specified as 0. In the future, it may be possible to use the argument to change the protection of a memory region affected by remap file pages. In the current implementation, the protection remains the same as the entire VMA. Virtual machines and garbage collectors are other applications that employ multiple VMAs. Some of these applications need to be able to write protect individual pages. It was intended that remap file pages would allow permissions on individual pages within a VMA to be changed. But this facility has not so far been implemented. The flags argument is currently unused. As currently implemented, remap file pages can be applied only to shared mappings. The remap file pages system call is Linux specific. It is not specified in SUSV3 and is not available in other Unix implementations. Summary. Cool. The mmap system call creates a new memory mapping in the calling process virtual address space. The mmap system call performs a converse operation, removing a mapping from the process address space. A mapping may be of 2 types, file-based or anonymous. File mapping maps the contents of a file region into the process virtual address space. An anonymous mapping created using the map anonymous flag or by mapping dev0 doesn't have a corresponding file region. The bytes of the mapping are initialized to 0. Mappings can be either private or shared. The distinction determines the visibility of changes made to the memory, and in the case of file mappings, determines whether the kernel propagates changes to the contents of the mapping to the underlying file. When a process maps a file with the private flag, any changes it makes to the contents of the mapping are not visible to other processes and are not carried through to the mapped file. A shared file mapping is the converse. Changes to the mapping are visible to other processes and are carried through to the map file. Although the kernel automatically propagates changes to the contents of the shared mapping to the underlying file, it doesn't provide any guarantees about when this is done. An application can use msync system call to explicitly control when the contents of a mapping are synchronized with the map file. Memory mappings serve a variety of uses, including allocating process private memory, private anonymous mappings. That's the most common use case that I've ran into, which is like heap allocation basically. Initializing the contents of the text and initialized data segments of a process, private file mappings. Sharing memory between processes via fork, shared anonymous mappings. Performing memory mapped I/O, optionally combined with memory sharing between unrelated processes. Shared file mappings. Two signals may come into play when accessing the contents of a mapping. SIG-SIG-V is generated if we attempt to access in a manner that violates the protections on the mapping, or if we access any currently unmapped address. SIG-BUS is generated for file-based mappings. If we access a part of the mapping for which no corresponding region exists in the file, i.e. the mapping is larger than the underlying file. Swap space overcommitting allows the system to allocate more memory to processes than is actually available in RAM and swap space. Overcommitting is possible because typically each process does not make full use of its allocation. Overcommitting can be controlled on a per mmap basis using the mmap that map no reserve flag, and on a system-wide basis using proc files. The mremap system call allows an existing mapping to be resized. The remap file pages allows the creation of nonlinear file mappings. Okay, we got 3 minutes. Let's check out the exercises. Write a program analogous to CP that uses memory mapping and memcopy calls instead of read and write to copy a source file to a destination file. Use fstat to obtain the size of the input file, which can then be used to size the required memory mappings, and use ftruncate to set the size of the output file. Rewrite the programs in listening 48.2, which is the writer, and 48.3, which is the reader, to use a shared memory mapping instead of a system V shared memory. I'm not going to do that. Write programs to verify that SIG-BUS and SIG-SIG signals are delivered in the circumstances described. Nope, not going to do that. Write a program that uses the map fixed technique described in section 49.10 to create a nonlinear mapping similar to that shown in 49.5. Don't care about that. Okay. The first one I kind of would be interested in doing, but given that it's already 12:30, I'm going to go ahead and call it. So, what page are we on here? It's 10:45. Yep. So 10:45, and it is 12:29. So I am going to break for lunch, and when I get back, it'll be about an hour and a half. So that put us at about 2 p.m. my time. I will resume reading the book at chapter 50, which is virtual memory operations. And then if I take a look at the index for the upcoming chapters, virtual memory operations, and then we get into some of the POSIX IPC stuff this afternoon. Cool. All right, I'll be back in about an hour and a half.